Thank you. So, good morning, everyone. This is Kian Chen from International Education Foundation. So I'm here to present the asymmetry theory mathematically derived from the principle of constant light speed. So the only starting point of this theory is the principle of the constancy of the velocity of light. I think everyone is familiar with this principle. Some quick definition. So this S is the origin of the light, and then O is the observer. Vs and Vo are their velocities, and Ts is the emission time, and To is the detection time. Based on this definition, this principle can be represented by equation 1, so very simple. And amazingly, there are so many important results can be mathematically derived from this single equation. And to clarify, asymmetry theory is not some idea that we fabricate. It's just a name that we gave to this mathematically derived result. And we will show some example of the results. So first, let me just summarize the asymmetry theory first. First one is strict mathematics only, so we didn't make any assumptions or postulations. Secondly, the result is comprehensive and self-consistent, so anyone can see that it's not some coincidence. And it's in harmony with all existing experiments. It provides mathematical explanations of key phenomena without any paradox. And Maxwell's equations provide theoretic proof of the theory. And finally, we designed 2 experiments based on its predictions so that you can check if the theory is correct or not. So now let's show some examples of mathematically derived results. First, this is the formula for the light speed, mathematically derived, and this is the formula for the light velocity. And based on this formula, the light velocity is independent of the emitter's motion. If Vo is 0, the light velocity is c. However, the velocity of light as to an observer is c minus Vo. So that's the most important result of this theory, which is mathematically derived. And now we can explain why we cannot measure the one-way light speed, because it's c minus Vo, it's not c. And for the round-trip light speed, it's almost c. If Vo is equal to the Earth's rotation speed, the difference is so small. That is why, MM experiment cannot detect the difference. So now let's look at the Einstein's clock. So that's the formula when the light speed is perpendicular to the motion. Our formula shows that the light speed is equal to c times the Lorentz factor. So it's very interesting that we see Lorentz factor here. And we follow the same Einstein's clock equation 7 here, right? The difference is that if you assume that the light speed is invariant, then you need the Lorentz factor to force fit this equation, so you have to value your time. But for our theory, that's our light speed, so we don't need to force fit the equation. Our time is invariant. So now let's talk about the Sagnac effect. So the experiment shows there's a delta t between the travel time of 2 light beams in opposite direction. This result contradicts the light speed invariance to moving observers. And we get a simple mathematical explanation, and the result is just because of the different velocity of these 2 beams, as you can see here. So we get very simple derived formula, which is exactly the same as the experiment result. It's important to say that it doesn't matter if there's an acceleration or not. And now let's talk about the observed time dilation and twin paradox. It's well known that the clock will appear ticking slower or faster if someone moving away or towards the clock, right? And the explanation is that it's just a time scaling factor, DTO divided by DTS. We call it observed time dilation just to avoid the confusion with the time dilation. And we mathematically derived the formula for this time scaling factor here. And based on this formula, there's no twin paradox. So the elapsed time of both clocks are always the same. It doesn't matter if there's acceleration or not. And the application of this observed time dilation, the Doppler effect is just simply a phenomenon of this observed time dilation. As you can see, we have a Doppler effect formula is equal to this DTO divided by DTS. And it will reduce to the traditional formula. It also predicts there's no frequency shift for circular motion, which is proved by 2 experiments. For the cosmological redshift, it's also a special case of this DTO divided by DTS. So we can derive exactly the same formula for this redshift. So basically, we explained everything in one single DTO divided by DTS. And Maxwell's equations provide theoretical proof of asymmetry theory. So this is the standard Maxwell's equation. It's important to note that this T here is actually TS. If we replace this TS with TO, then we get another format of Maxwell's equations. It's very important to understand that this 14 is exactly the same as 12. It's just a different format with TO as the time variable. It's not a new equation. If we solve this Maxwell's equation, we get the formula for the light speed and the formula for Doppler effect. They are exactly the same as what we derived before. And we also proved that the Maxwell's equations are covariant under Galilean transformation. So now let's talk additional example about the electrodynamics that we mathematically derived. So we all know that particles can't accelerate past c. And this one can be explained by our formula of the momentum to acceleration ratio. As you can see that when VO approaches c, this ratio will approach infinity. That's why it cannot be greater than c. The difference between asymmetry theory and the special relativity, as you can see, is that one is symmetric and another one is not. That's one reason that we call it asymmetry theory. And we also mathematically derive this energy mass relationship formula here. And this is consistent with other theories. So as we all know that the experiment is the final judgment for any theory. So we designed 2 experiments based on the prediction of the theory. So first one is to test the light speed invariance to moving observers. So we have 2 observers moving at speed v here, and we will measure the detection time of these 2 sensors. Our prediction is that there will be a delta t between the measured detection time. And then another experiment is very simple. Just use the momentum to acceleration symmetry that we talk about. So assume a particle with a speed of 0.c, and you switch the direction of the accelerator. Then our prediction is that you will see immediately a 3-time jump of the momentum to acceleration ratio. And other theories predict there's no change of the ratio. So these 2 experiments are straightforward. If you are interested, you can just implement it and then to check if the prediction is correct or not. These are just some examples of the result that we derived. So for more results and more details, you can find the 2 papers in this location, and this is my contact information. Thank you for your time, and any question?
Thank you very much for the talk.